Understanding the communication models in 5G. Hello and welcome. In this training, we'll start by exploring the fundamental ways network functions, or NFs, communicate with each other in the 5G core network. This communication is based on two primary models: request, response, and subscribe, notify. These models are built upon the principles of representational state transfer, REST, using HTTP/2 as the underlying protocol. The request/response model is the most common and direct form of interaction. It's a synchronous process where a service consumer sends a request to a service producer and then waits for a response. Think of it like making an API call on the internet. A web browser requests a specific piece of data from a server, and the server sends back that data. A perfect example in 5G is when the AMF, Access and Mobility Management function, needs to set up a data session for a user. It sends a direct request to the SMF, Session Management function, and waits for a response indicating whether the session was successfully established. In contrast, the subscribe/notify model is designed for event-driven communication. Instead of constantly checking for status updates, a service consumer can subscribe to an event with a service producer. The producer then only sends a notification to the consumer when that specific event occurs. This approach is highly efficient and reduces unnecessary signaling. For example, a PCF, policy control function, might need to know when a specific data usage quota has been reached for a user. Instead of constantly querying the SMF, the PCF can subscribe to a data usage threshold event with the SMF. The SMF then notifies the PCF only when the user's data usage reaches the predefined limit, allowing the PCF to enforce a policy like throttling the user's speed. The NF service framework. With these communication models in mind, let's look at the NF service framework, the set of rules that governs how all the NFs in the 5G core discover and interact with each other. This framework is a core concept that allows for a flexible and modular network architecture. At its heart, the framework is about a simple yet powerful relationship between a service producer and a service consumer. The producer is an NF that offers a service like the authentication server function, AUSF, which provides authentication services. The consumer is an NF that needs to use that service, such as the AMF, which needs to authenticate a user. The framework provides a clear three-step process: registration, discovery, and communication. First, a service producer registers its services with the Network Repository function, NRF, which acts as a central directory or a yellow pages for all available services in the network. This registration includes details like the NF's identity and its network address. Next, a service consumer queries the NRF to discover the producers that offer a specific service it needs. For example, an AMF queries the NRF to find an available AUSF. Finally, once the consumer has the producer's address, it can directly communicate with it using the defined communication models and API we just discussed. This framework creates a loosely coupled network where NFs don't need to know the specific details of other NFs in advance, making the network highly scalable and resilient. The Service-Based Interface SBI. The Service-Based Interface SBI is the technical realization of the NF service framework. It is the logically shared bus that allows network functions to expose their capabilities as services to other authorized NFs. Think of it as the common language and set of rules that all NFs must follow to communicate effectively. The SBI defines a standardized set of application programming interfaces, APIs, using web technologies like OpenAPI specification, formerly Swagger, HTTP2, and JSON. This approach provides several key benefits borrowed from cloud computing and IT. It ensures interoperability between equipment from different vendors, enables a modular and scalable network by allowing individual NFS to be added or removed easily, and provides abstraction by hiding the internal implementation details of a specific NF from a consumer. The SBI is the language of the 5G core, connecting all the different functions like the AMF, SMF, PCF, etc. in a consistent and agile manner. The N27 interface. Finally, let's look at a specific and critical interface, the N27 interface. This interface is used for communication between two network repository functions, NRFS, specifically between a home network and a visited network. The N27 interface is essential for enabling global roaming. When a user roams from their home network to a visited network, the NFs in the visited network need to communicate with the user's home NFs, such as the Unified Data Management, UDM, and Authentication Server function AUSF. The NRF of the visited network uses the N27 interface to query the NRF of the home network. This query allows the visited NRF to discover the addresses of the home NFs, enabling the visited network to authenticate the user and provide the requested services seamlessly. The N27 interface ensures that service continuity and communication are maintained for users even when they are a world away from their home network. In summary, the 5G core's flexibility and efficiency are built on a robust set of principles. The NF service framework enables network functions to discover and communicate with each other, using the service-based interface SBI as their common language. This is all supported by two key communication models: request, response for direct interactions, and subscribe, notify for efficient, event-driven communication. Lastly, the N27 interface plays a crucial role in extending these principles across different operator networks to support seamless global roaming.